Hey everyone, I thought I would go through the solutions to the first actual graded quiz. I'll be posting this and also my solutions to the math quiz, along with some explanations as to why they are what they are, sometime this afternoon, hopefully pretty quickly, if I can get these videos done quick and produced. Alright, so let's see. Number one on reading quiz 1. We have a race car that starts from rest, so VI is 0. Then it accelerates at a constant 5 meters per second squared. And we want to figure out how fast it's going in kilometers per hour after traveling 100 meters. So let's see, let's call 100 meters delta x. Note the decimal point after the 0 here. That's to indicate that this is actually 3 significant figures. If we didn't have that, that would just be 1 sig fig. Okay, so with that in mind, for this one, what do we know? We know initial velocity, we know acceleration, and we know distance traveled. So we can use our time-independent kinematic equation to work this out. So that one is the Vf squared equals Vi squared plus 2a delta x. And all we need to do here is just take a square root of both sides, so we can have Vf is equal to the square root of Vi squared plus 2a delta x. And let's substitute. So let's see. We know Vi is 0, so that's just 0 squared. Then we have 2 times 5 meters per second squared times the distance, which was 100 meters. All under that square root sign. So this winds up being essentially the square root of 1,000. And if we do our meters correct, or our units correctly here, the units on this are actually meters squared per second squared, which makes sense. We're taking the square root, so that should give us meters per second. So the velocity in meters per second is going to be 31.6 meters per second. But that's not all. We need to convert to kilometers per hour. And we can do that using dimensional analysis. So let's see, we have our 31.6 meters per second. Let me write this in a slightly different way. 31.6 meters per second. Then, let's see, we want to cancel the seconds and replace it with hours. So we know 3,600 seconds are in 1 hour. And we want to cancel the the meters and replace it with kilometers. So we know that 1 kilometer is 1,000 meters. And when we do out this multiplication, we should find that the velocity in kilometers per hour is about 114 kilometers per hour. So that's how you do number 1 on the reading quiz. All right, here's number 2. So we want to find the average velocity of the race car. And we're finding it in meters per second. Okay, so the average velocity, v bar, that's a kind of drew those close together using the marker, but that's just a v with a bar over it, not a vector arrow. So the average velocity of the race car is going to be this. So we can call average velocity just the final velocity plus the initial velocity over 2. And we want this in meters per second, so instead of using the 114 kilometers per hour that we calculated as our final answer to number 1, we'll use the 31.6 meters per second that we calculated on our way to calculating 114 kilometers per hour. And its initial speed was 0. So we divide by 2, and we should find the average velocity of the race car to be 15.8 meters per second. All right, number 3. Number 3, we have a dropping a rock from the edge of a cliff. I'm going to draw this out a little bit, so maybe you can. So here's the cliff, and here's the rock falling down. And it's going 40 meters per second when it hits the ground and it's dropped, which means it's basically assuming, we're assuming that if it's dropped, it starts from rest. So Vi equals 0, and Vf equals 40 meters per second. 40 meters per second when it hits the ground at the base of the cliff. So it turns out we can work out how high the cliff is in meters based on this. So what do we know? We know Vi, Vf, and we also know, though it isn't said explicitly in the problem, that since it's falling under gravity, the acceleration should be just negative g, which is negative 9.81 meters per second squared. So we have everything we need to calculate the height of the cliff. And we're going to use our time-independent kinematic equation. But this time, we're not going to solve for velocity or acceleration. We're going to solve for, I guess, delta y in this case. So we'll write this in terms of y rather than x. Vf squared equals Vi squared plus 2a delta y. We want to solve for delta y. So delta y equals, let's see, Vf squared minus Vi squared over 2 times the acceleration. So Vf we know to be 40 meters per second. Let's call that minus 40 because it's falling downwards. Doesn't really matter because we're squaring it. It was dropped from rest, so its initial velocity is just 0 meters per second. We have 2, and then we have the acceleration due to gravity. Okay, so let's see. Calculating all that out, negative 40 quantity squared is going to be 1600. 2 times negative, or 9.81 is going to be about 19.6. You can put the exact numbers into your calculator, and you should find that delta y equals negative 81.5 meters, which means that the rock fell 81.5 meters from the top of the cliff to the ground. So the height of the cliff is 81.5 meters. All right, number 4 works with the same cliff. So let's, all right, number 4. We want to find out now how long it takes the rock to fall that distance. In this case, 81.5 meters. Okay, so we now explicitly need to find time, so we can't use our time-independent kinematic equation. But what do we know? We know YF, we'll call that 0. We know YI is 81.5 meters. We know VI equals 0 meters per second. VF equals, call that negative 40 meters per second. And A equals negative 9.81 meters per second squared. So we know a lot of stuff. And it turns out we can use a number of equations to figure this out. We can either use our position kinematic equation, YF equals YI plus VYIT plus 1/2 AYT squared, or we can use our velocity kinematic equation. And that would just be VF equals VI plus AT. So I think it's easier to use this one because we don't need to solve a quadratic equation. So we know VF is negative 40 meters per second. We know, actually, you know what? I'm going to solve that for T first, sorry. So T is just going to be VF minus VI divided by acceleration. So let's see, plugging that in, we have negative 40 meters per second minus 0 meters per second divided by our negative 9.81 meters per second squared. So negative signs cancel, we get 40 over 9.81, and that should give us a time of 4.07 seconds. So it just takes a hair over 4 seconds for the rock to reach the bottom of the cliff. All right, for number 5, we've moved into actual projectile motion. Get my papers rearranged a bit. Ooh, a lot of blue dots on there. Problem with Sharpies is they bleed through. Okay, number 5, we have a golf ball that's being struck off the tee at a velocity of 30 meters per second and an angle of 60 degrees to the horizontal, and we want to figure out first how long it's in the air. Okay, so this is going to involve us solving a quadratic equation, I can tell you that right now, but let's write down what we know. We know that VI is 30 meters per second, and we know that theta is 60 degrees. And we want to find t. What else do we know or can find out? Oh, stupid camera. Okay, so it's a projectile, so we know that for the acceleration, AX is 0. There's no acceleration happening in the horizontal direction. But in the vertical direction, AY is going to be negative 9.81 meters per second squared. So that just represents the force of gravity pulling down the ball as it flies. We're also going to assume that it starts at ground level, so we'll call xi and yi both to be 0, and because I specify in the problem that it's a level course, we'll also take yf equals 0. Okay, so what do we need to find to figure out how long it's in the air? Let's write down our position kinematic equation for y, for its vertical position. So we know yf equals yi plus vyi t plus 1/2 at squared. I probably should write that as minus 1/2 gt squared, but we'll worry about that when we substitute. That's a subscript y, not a g. Okay. So we know it starts and finishes at ground level. So 0 equals 0 plus vyit minus 1/2 gt squared. So we need to find vyi first. Fortunately, we can find that given what we know. We know the angle it's hit at, and we know what vi is. So vyi, remember how our vector components work, is just going to be vi times the sine of 60. So we'll have 30 meters per second times the sine of 60 degrees. And that'll give us an initial y velocity of, sorry, let me plug that into my calculator here. 26 meters per second. 26.0 meters per second, actually. What else? Okay, so we can substitute that in and get a quadratic equation. I'm going to suppress the units and significant figures just for the sake of making the quadratic equation a little easier to read. So it's going to look like this. We'll have negative 4.905. This is the 1/2 g. Then we have t squared. Then we have our initial velocity, 26 times t equals 0. So we can actually solve this by factoring. Makes things a little easier. We don't have to plug into the quadratic formula. So if we pull out a common factor of t, we can rewrite it like this. 4.905 t plus 26 times t equals 0. Well, that gives us one answer right away. Yeah, t equals 0 as a possible solution, but that's when the thing starts. So it's obviously at ground level when it starts, so that's not a useful piece of information for us. So in order to find the actual time it's in the air, we need to solve this equation. Fortunately, it's not a quadratic equation, it's just a linear equation, so we can just plug and chug. So let's move on to that. So I'll put this off to the side. So we have negative 4.905 t plus 26 equals 0. And if we solve for t t equals negative 26 over negative 4.905. And that should give us a flight time of 5.30 seconds. So that's how long it's in the air. That's the first part. This is number 5. All right, number 6. Number 6 is still using the golf ball, and this time we figured out how long it's in the air for. And now we want to find its maximum height, find Ymax. Now there's a general way to do this, and then there's a shortcut that we can use in this problem. And the shortcut is this. YF is equal to YI. The golf ball starts and ends at ground level. It doesn't have to be ground level. In this case, it's ground level. It's as long as they start at the same level, then we have symmetry. Because the trajectory of the golf ball will look like this. It'll just be a nice, here's where it hits the ground. Nice parabola. And so that means that when it's at its maximum height, at half its flight time. And Tmax is half the total flight time. So what that means is we can calculate our Tmax, which is just going to be half of 5.3, which is going to be 2.65. So Tmax is 2.65 seconds. Then we can just plug that into our vertical position kinematic equation. So Ymax is Yi plus Vyi Tmax minus 1/2 G Tmax squared. And everything in here we know. We know Yi is 0. We know what we calculated Vyi to be 26 meters per second. We know that G is 9.81. So just substituting in those numbers real quick. 0 meters plus 26.0 meters per second times our Tmax, which is 2.65 seconds, minus 1/2 times 9.81 meters per second squared times 2.65 seconds squared. All right, this is the one point we're going to want to be careful. Remember, you have to square the time factor here on the acceleration term. A couple of you forgot to do that in your quiz solutions. So keep that in mind when you're doing projectile motion. You need to square the time factor on the acceleration term. And when all of this is worked out, we find that the maximum height of the golf ball is 34.5 meters. Okay, so here's the last question on the quiz, and it also has to do with the golf ball, and we want to figure out how far it's going to go. We want to figure that out in meters. All right, so this is the easy part of projectile motion problems, is finding out how far it goes, because we just want to find xf equals xi plus vxit plus 1/2 a sub x t squared. Well, the nice thing about projectile motion problems is that the x acceleration is always 0. So we can just get rid of that term entirely. And we also know that xi equals 0. So xf is just going to be vxi times the time of flight, and that's it. And we haven't found Vxi yet, but we can find it pretty easily. Vxi is going to be Vi cosine theta. In this case, Vi is 30 meters per second, and theta is 60 degrees. And I just happen to know that the cosine of 60 degrees is 1/2, so that gives us that Vxi is 15 meters per second. Then, we already have time of flight, so we just need to plug that in. So xf is just going to be 15 meters per second times our time of flight, which we already found to be 5.30 seconds. And that should give us a distance of 79.5 meters. And that's it for the quiz. If you have any questions about any of these problems or want me to go into more detail on what I'm doing and why, let me know either on email or post a question on the discussion board for the class. Hopefully this will go up pretty soon, along with the math assessment quiz solutions.